All right, so in this video, we're actually going to be looking at a really nice statement that has this kind of neat little connection between odd numbers and their squares. In this situation, we're going to claim that if n is some odd integer, so whatever odd number you want to start with, if you compute its square, in this case n squared, I'm going to claim that it's also going to be an odd integer. So the goal of this is going to be, we're first going to start to kind of play with this statement a little bit, running enough kind of tests to see that this may actually be somewhat believable. But as we know that running just a bunch of little tests is not going to be good enough to actually say that this is true in general, so we're going to have to lead into an idea of kind of building up a really nice valid argument that says, yes, if you start with any general odd number, if you compute its square, it's also going to be an odd number. So in this situation, we're going to build up a little no-show table and then ultimately try to write this thing down as a formal proof. But before we go into that, like I mentioned, we're going to kind of dig into this statement a little bit to try to get our hands dirty to really see what's going on in this situation. So the idea is that I should grab whatever odd number I want to start this thing with. Well, a really easy odd number to start with is going to be, I don't know, let's say 1. It's probably the easiest odd number that I can think of. If you take this 1 and you try to square this thing, well, what's going to happen is you're just going to have 1 squared, which is 1, which is also odd. Well, in this situation, we've only tested one example, which is nowhere near enough to kind of get a good feel that this is actually believable. So what I'm going to do is I'm going to just cycle through a bunch of different types of odd numbers. In this case, I'm just going to do it with kind of pencil and paper, or I guess tablet and stylus, but just kind of working away on kind of some scratch paper to see what's actually happening. If you're interested, you can come up with a little for loop in Sage or whatever your favorite programming language is to kind of test through all of these odd numbers that you can kind of think of up to a certain stage to really see kind of that this does in fact appear believable. But in this situation, we'll just do it kind of old school paper and pencil way. So the next kind of odd number I'm going to look at is, well, let's just look at the next one, which is going to be 3. And if I take 3 squared, I know that that's going to kick out a 9, which is going to be odd in this case as well. If we go up, let's just say one more, I'm going to look at 5, and if you take 5 squared, what's going to happen is that that's going to kick out 25, which is odd as well. And if you keep on going to larger and larger odd numbers, you're going to see that you're constantly going to be kicking out these nice squares of these odds, which is still always going to be odd. What you should always do is anytime you're working with this very just general concept of an integer, you should always test the negatives. The negatives a lot of times are going to be where counterexamples may actually live. And we know that if we can find a counterexample, then our work is pretty nice. I can say, here's this example that breaks whatever statement you just gave me. So in this situation, your statement is not actually true because this is the thing that breaks it. In this example, we're actually not going to be able to find a counterexample because that statement is actually going to be true, but we should at least see what's happening in the negative world to understand why the negatives are not a big problem in this situation. So let's test just a random negative number. In this case, let's look at -1. Well, if I take n squared in this case, it's just going to be -1 squared. And here's where you can see that the negatives really don't matter at all. -1 squared is the same thing as 1 squared, and we know that 1 squared is 1, which is odd. But just for kind of completeness, let's look at -3. If I take -3 squared, which is just going to be the same as 3 squared, it's going to kick out a 9, which is also going to be odd. So in all of these situations, it at least appears believable that this result may actually hold, which is why we give this thing a fancy name referred to as a conjecture. So in this case, all a conjecture is just going to be one of these statements that we seem to have done enough examples on that it appears that it might be believable. It is not kind of been formally shown yet, but at least it's enough that I've done a bunch of examples and I can't find a counterexample yet, but it's not saying that a counterexample exists somewhere else. It's this idea that I've done enough to kind of give me a good gut feeling that it should work, but I still have to come up with the actual valid argument. So what I need to do in this situation is then think about what's really going on in this situation. The idea is that I should be able to start with any general odd number. And that's where the kicker is that there are infinitely many odd numbers. So I can't kind of write an overly exhaustive for loop that's going to test every single possible odd number because it's not possible to test every single thing. There's always going to be another thing you have to test because that list is going to go on and on and on and on. So what I need to do is I need to start thinking about doing this a little bit more generally. And what's going to happen is I want to think about what general odd numbers look like. So odd numbers have a really special property. Well, the first property is that they're not even. But that's exactly where an odd number comes from. The idea is that if you take some even number and you add 1 to it, that new thing is actually going to be a very nice odd number. And that's exactly what the definition of an odd number is. So down here below, I'm going to actually have this formal definition of being odd, which will go back and show kind of why this definition works in this kind of initial observation that we have. So the idea is that some number n is going to be odd if it has this property that it's going to be an even number, which even numbers are really easy to build. You just take whatever number and multiply it by 2, and you're going to have an even number, and in this situation, you just add 1 to it. So in the next video, we're actually going to go through and show kind of what the definition of an even number is, but it's really going to be the same as this odd, except for don't add 1 to it. So to kind of make sense of this definition, let's go back and see if those numbers that I looked at can actually be represented in this somewhat funky form of 2k plus 1. So the idea is that 1, I want to view this as 2 multiplied by some number plus 1. Well, in this situation, what it's going to be is it's going to be 2 times 0, in this case, plus 1. So it's the idea that the easiest even number you can think of is 0. So 0 plus 1 is exactly how I get 1. Next up is going to be the number 3. Well, I know that 3 is just 1 more than 2, so I'm going to take 2 plus 1, and that's going to become my 3. Next, I have the number 5. 5 has a special property that it is 4 plus 1, and 4 I can represent as 2 times 2 plus 1. The weird stuff actually ends up happening once I go down this negative world. The idea that negative 1 is actually going to be negative 2 plus 1, which I can represent as 2 times negative 1 plus 1. Likewise, negative 3 is going to be negative 4 plus 1, which is going to be 2 times negative 2 plus 1. So in all of these situations, you can see that these numbers are of the form 2 multiplied by some integer, in this case k, plus 1. So this ability of making these kind of odd numbers look really general is going to be the big component of actually trying to show this thing. If you start with something that just looks like 2k plus 1, that's going to encompass all possible odd numbers. The idea that k can do whatever it wants to do, in this case, cycle through anything you want it to, in this case, any integer, this is going to give me this special property about being odd. Later on in the course, we're actually going to start to generalize this idea a little bit farther. This is where some of this modular arithmetic is going to come into play. This is this notion that odd numbers, modulo 2, are going to kick out 1s. So for those of you in the programming world, you're going to start to see this modular arithmetic a little bit earlier, but in this case, we're going to see this later in this course as well. It's going to be this really nice test of whether or not a number is odd or even. And it's exactly, you're going to have 2 times some number, in this case plus 1, and if it happened to be even, you're just going to have a plus 0 afterwards. So once you kind of internalize this notion of actually being odd, that's actually going to be most of the kind of battle that we're going to play. So what we're going to do in this situation is come back to this actual kind of argument and try to make this a little bit more formal. So the idea is that my initial assumption, my hypothesis, is going to say that n is going to be some odd integer. So it's going to look like 2k plus 1 for some integer k. The goal then is going to say my conclusion should be that n squared is also going to be an odd integer. The kicker here, and the thing that students seem to mess up a lot of times right away, is that it's not going to be the same k. It's going to look like some other 2 multiplied by a different k plus 1. So notice the difference in this situation. I'm going to start with a general odd number, which looks like 2k plus 1, and then my goal is going to be to square that thing and then turn that into an odd number, which in this case, the little k is actually going to be different. And you can actually see this example emerging in that last example that we just saw. So in this situation, if I look at something like n being, let's say, 3, I know that 3 is actually going to be represented as 2 plus 1, which is viewed as 2 times 1 plus 1, whereas n squared, which is going to be a 3 squared, is going to be a 9, and I know that 9 is actually going to be represented as an 8 plus 1, which is viewed as 2 times 4 plus 1. So you can see in this situation that my initial value, let me switch colors here, my initial assumption is going to have my value of k, which is going to be a 1, compared to my squared term is actually going to have a k value of 4. And you can see that there's a mismatch in these two things. So what I typically like to do is I'd like to, instead of using this initial k that we start with, the new thing I'm going to switch, and I'm just going to simply call it an L. So I'm not confused by kind of seeing what's happening. My initial expression is going to have one value of k, but my new thing that I'm going towards is going to have some other value of k. And it's somewhat unfortunate that we use k's over and over and over again, but the idea is that it's going to be just some general integer. Call it whatever you want. So in the initial case, it's going to be n is an odd number, so 2k plus 1. And my goal is going to be that n squared is going to be an odd number. In this case, a different k, so I'm just going to call it an L. Some students like to say n is going to be a 2k1 plus 1. In this case, n squared becomes 2k2 plus 1. If they really like to use this notion of different k's but still keeping that k structure around, that's totally fine as well. I will typically use k's and l's or m's and n's, things like that, just kind of general letters that are going to represent these very general notions of an integer. So what we're going to do next is actually come up with a little kind of diagram of what's going to happen is that I'm going to come up with a bunch of little steps that are going to try to link my initial assumption to my overall final conclusion. What this is going to be referred to as is a no-show table, and it's going to give us a little bit of structure of what's underlying all of this. And once we have this little no-show table built up, we're then going to come back and try to write this thing down as a formal proof. So in this situation, what's going to happen is that I'm going to kind of identify a step in this kind of very far left column. What's going to happen is that in the middle part, it's going to be the part that I know. So I'm going to put the word know in it. And then way over on the right, I'm going to have my reason. So if you remember back to some of your geometry classes or maybe a trig class or something like that, you probably have seen these types of kind of two-column proofs. It's this idea that I'm going to try to come up with a lot of kind of natural connections between my starting place and my conclusion. It's going to fill in the gaps. And the idea is that you can start on the top and you can start on the bottom and kind of slowly work your way inward. So what's going to happen is that my initial step, my initial assumption is going to be that n is odd. And my reason for that is going to be my hypothesis. And my very final part, and hopefully I'm leaving enough room, is going to say that n squared is odd. And that's going to be my conclusion. So my goal is going to be to connect all of those little pieces in the middle. And then this is where a little bit of algebra is going to come into play, as well as some of these properties of these integers. So the first thing that I can do is, if I'm starting with this assumption that n is odd, I can make the change from just a general n, which is sometimes hard to work with, to this expression that looks like 2k plus 1. So I'm going to say that n equals 2k plus 1 for some integer, in this case k. And that is exactly using the definition of odd. So that is the definition of odd, in this case applied to the kind of n, this initial n that we started with. So now what's going to happen is that I'm going to try to manipulate this expression into something. I have to do the squaring process at some point in time, but my goal is going to be to get down to a stage that n squared is going to look like a 2l plus 1. And that's also going to be using this definition of odd. And this is going to be on n squared. So you can see that I'm working a little bit from the top, I'm working a little bit from the bottom, trying to connect the dots along the way as I go. So what I'm going to do next is I'm actually going to introduce this notion of the square. I've kind of exhausted all I could with this idea of what n looks like. Well, now I'm going to go into the stage of what does n squared look like? Well, n is now 2k plus 1, so I'm going to substitute that in for my n, and there's still going to be a square on the outside of that. Well, now I'm just going to use a little bit of algebra. Anytime I have a square, I'm just going to write these two binomials next to each other and then do this kind of classic foiling step afterwards. So I'm going to have 2k times 2k, which is going to kick out a 4k squared. The outside part's going to be a 2k, the inside part's going to be a 2k, and when you add those together, you get a 4k. And then the very last little bit, there's going to be a little plus 1. So these steps are going to be identified as a substitution. There was a little bit of algebra. I guess there's just a little bit of algebra occurring here as well. Just a little bit of kind of simplifying, really seeing what the underlying structure is going to be. And now I'm actually going to change colors just slightly in this world. I'm going to look at this expression, and I'm going to look at this expression, and I'm going to try to bridge the gap. I want this thing to have a little plus 1 at the end, and you can see that I do have a little plus 1 at the end. So that 1 is good to see. What I need to see is I need to see a little 2 multiplied out in front of everything. Well, if you look at that, there's a 4 here and there's a 4 there. What I can do is I can sneakily factor out a 2. And I'm just going to factor a 2 out of those first 2 terms. In this case, I'm going to leave a 2k squared plus a 2k behind. And the idea is that this thing looks like this thing down below. It's just written kind of funky. There's a 2 multiplied by blah plus 1. And that's exactly what the idea of being odd should be, is it's going to be 2 multiplied by blah plus 1. So that's exactly that key step that's going to make all of this work. And that step is going to be identified as a factoring step. So now we're just going to clean things up a little bit. What's going to happen is that I'm going to identify this little portion on the inside. I'm going to say that that thing is my L, which is going to be a 2k squared plus 2k. And I'm going to make a very big claim at this stage in that this is actually going to be an integer. Is an integer. And that's really what makes all of this work, is that no matter what, you could always factor a 2 out of whatever you want to. The big kicker is that whatever you're left with has to actually be an integer. The idea is that if you lose this fact of being an integer, everything is actually going to break down. The example that I kind of sometimes go to is that I can actually make the number 4 pretend to look like a very nice odd number. The example would be that I'm going to write 4 as a 3 plus a 1, and what I want to do is I want to see some 2 in front of that thing. Well, I can factor a 2 out of that 3. All I have to do is just factor a 2, and then what I'm left with is a 3 halves plus a 1, and you're like, oh, this thing looks like 2k plus 1. The problem is, though, is that this little 3 halves is not an integer. So it fails that really big assumption. So in this case, if I break that thing down, seeing some type of division or something like that, I have this world that I might not actually be dealing with an integer. So in this case, you do want to make sure that you have this big key step that's going to say whatever operations you did not leave the realm of being an integer. So here's where you're going to have this notion of kind of multiplication and kind of squaring and addition. None of those things are going to break this integer world, whereas division and things like that have this potential to bring about fractions. So those are going to be the things that you're going to want to be on the lookout for, is don't try to do those operations, just do this adding and squaring and all those kinds of things, and everything's going to be okay. With this 2k squared plus 2k is in fact going to be an integer. And the reason for that is that we're actually using this notion of closure. The idea, I'm actually missing an E. The idea is that everything that's involved in all of this stuff is actually not going to break down any of these properties about keeping an integer. K was an integer to start with, so if I take this multiplying by 2, that's going to keep an integer. Squaring is not going to change anything. Everything that's involved in that step is going to keep this notion of being an integer. So here the property is going to be this closure of the integers. And that's the big step that makes everything work. So now we have this nice little connection. I'm going to start with some odd number. It looks like 2k plus 1. If you square that thing and do a little bit of algebra, what's going to happen is that I can transform this thing into something that looks like 2 multiplied by blah plus 1. And that blah is in fact going to be an integer. I didn't do anything that actually violates this notion of being an integer, so everything works out nicely. It's 2k squared plus 2k. That thing I'm just going to call my L, and now it exactly looks like this is going to be a 2L plus 1, which is exactly what I wanted to see down below. So in this step, we do a bunch of these little processes against this kind of n value initially. We squared it, slowly working towards this n squared. I'm going to swipe it to the next page just because I do have a slightly cleaner version of this no-show table, and this is the one that actually exists in the notes as well, just to kind of go away from some of my chicken scratch as we kind of re-walk through some of these steps. So the idea is that you're going to start with an odd number. Those odd numbers look like 2k plus 1 for some integer k. If you do a little bit of substitution in algebra, that is substituting 2k plus 1 for n and then squaring it, what's going to happen is you get this 4k squared plus 4k plus 1. I want to see this little plus 1 because that's the plus 1 that's going to emerge down there. The next little bit is I want to see a little 2 emerge, and that's going to be the 2 down there. And so what's going to happen is that you're going to have to factor out this bit that says 2k squared plus 2k. Give that a fancy new name, which in this case I'm going to call an L. That thing is going to stay an integer because I know this nice closure of the integers. Underneath multiplication and squaring and all of that good stuff, I'm not going to lose this fact that I'm an integer. So everything at the end of the day is going to funnel into the fact that n squared is in fact going to be odd. So next up, I'm going to actually dive into trying to write this thing up in a nice little paragraph. And I'm going to do that in a separate video just because this one's already getting pretty long. But the idea is that I can take this and construct a really nice little paragraph to kind of streamline all of this conversation to really come up with this nice justification on what's going on.